Okay, so we are on page 63. Page 63, we are ready to do example number 4. Using theorem number 2, which is the polynomial and rational function. So let's look at that first. Read through on that, see if that makes sense to you. Okay, there's a 1 and a 2. So basically on a polynomial function, if you have limit and x is going to c, you're essentially replacing the x's with constant c, correct? All right, because that's the limit, right? Okay, all right. And then it's the same thing when you have the polynomial divided by another polynomial. It's the same thing. Right? So let's see if we can do this. Let's go if we can do example number 4. So we'll do example number 4 here. Example number 4, we have a limit as x goes to 3 and the function is x squared 2 minus x. Okay, so again, this is the function. And as x approaches 3, so we're just going to put 3 in here, and we're going to say, well, this is 3 squared 2 minus 3. Simple as that, right?
Is that easy?
Right? Is that easy? And then we go, the next one is example goes to 2. Limit as example goes, as x goes to 2, I have x squared plus 2x plus 4, is that correct?
Mm-hmm.
There's an x plus 2 on the bottom.
Mm-hmm.
Okay, so here we go. Again, where x is, I'm just going to put the 2 in, so I'm going to get 4 plus 4 plus 4 over 2 plus 2. 12 divided by 4. Okay. All right, so that's that. Example number 5. Okay, example number 5 is a little tricky. Example number 5, we want the, as x goes to 0, tan x, right? So it's 5. So we have limit as x approaches 0, we have x over tangent x. Okay, remember last time we did this, limit as x approaches 0, sine x over x, right? And we said that we looked at the graphing calculator and it said what? This was 1, correct? Remember doing that? Okay, we did that, all right? So we're going to use that fact here. Okay, the way we're going to do this is we're going to say, well, tangent x is actually sine x over cosine x over x, right? And I know that this guy here approaches 1. Right? What happens to cosine x as it approaches 0?
1. 0. 1.
Cosine x goes like this.
1.
Right, so as x approaches 0, it's going to approach 1. Right? So you get 1. So you're going to have 1 divided by 1. So it's 1. Okay? The reason why I can't just go put it in is when what do I have? If I put 0 here, what do I get?
0.
What do I get here?
0.
0 divided by 0.
0.
Not a good thing, right? Okay?
No bueno.
Okay. All right, so that's that. And then we have one more of these. Okay. We have one more of these. And I have, example number 6, I have x cubed minus 1. X is going to where? 2. X cubed minus 1, x minus 2 is equal to 0. Example number 6. So I put 2 in here, what do I get?
8.
8 minus 1 is
7.
What do I get here?
0.
2 minus 1 is 1.
2 minus 2.
We can't do
Oh.
0. Okay? Alright? So let's go ahead and graph this and tell me what you get.
I don't have my
Okay.
calculator.
What a surprise.
We learned this at the during physics when we were taking the test.
Everybody just hates on me.
How do you feel about the physics test?
Oh, I'm gonna go ahead and drop that one because I'm sure that's gonna be
Wait, you guys did drop one in school?
yeah.
Here we get to drop 1 score.
In the semester.
So maybe, do you get to pick at the end of the semester?
Yeah,
I
our
think
lowest
so.
score we get to pick one to drop.
What happens if you pick to drop this one and then there'll be
I
a
sure
test
hope
grade?
this is this. I don't know. I don't know what to do.
That's not what I got.
Do you have something close to this?
Wait, we put in the calculator?
Not at all.
I got that.
How?
She didn't get it.
Well, I kind of
I
got
got the
like
same thing Ellie got.
Well, that's not what it
Are you in
is.
radians?
No, it doesn't matter.
Hold on, Mr. Owen.
That's what I got.
yes. Me and Abby got the same thing, Mr.
Open up your window a little bit.
Oh, okay.
I got one that's wrong.
Mr. Ron, did I do it?
Oh, I got it. You just have to zoom out.
Did it show up?
It's just
When you
really high
zoomed
up.
out?
I got
It
this.
showed up?
Oh, you don't need to put the one.
Do not even more.
I don't think it's right.
Good.
Oh.
You got that? You got that? You got it? Tanner, you're good?
No, mine won't pick it up.
Okay, so what do we have here? We actually have an asymptote, which makes sense.
Right.
Because we learned last year asymptotes happen when the denominator goes to 0, correct? Okay, so last year what we also learned is we talked about one-sided limits. Remember that?
No.
So if I ask you if this is f of x, this is f of x, limit as x approaches to f of x, but I'm going to approach it from the positive side. If I approach the 2 here from the positive side, the function is going to go, correct? Right? Because it goes up like that, all right? Limit as x approaches 2 from the negative side. From the negative side, this is going to be
Oh my god.
negative infinity.
Mr. Ron,
Correct?
I didn't get that though.
Hmm?
Oh.
I fixed the window.
Wait,
Okay.
But
So, you can see that how the one-sided
Is the window?
are different.
so
Right.
there is no one.
So yes, exactly. When the one-sided limits do not coincide with each other, then you have a DNE situation. Does not exist. The limit does not exist. For a limit to exist, the one-sided limits have to coincide with each other, okay? So if you go flip the page, go to page 64, there's a theorem number 3. So read that.
Whoops.
And see if that makes sense
There
to
we go.
you.
Theorem 3 on page 64.
Okay, we good?
Yeah.
All right, let's get example number 8. Exploring left and right-handed limits. So let's go ahead and follow this here. So at x equals to 0, what is my right-hand limit?
Hold on. What?
SX.
Limit as x approaches 0 from the positive side.
1.
What is it?
1.
Positive side
1.
1, correct?
Mm-hmm.
At 1, what is my limit when I'm coming from the positive side?
2. 1. 1. 1.
1, right? Because from here, I'm approaching here, so it'd be 1, right? What is my limit at 1 from the negative side?
0.
0. In other words, a limit here does not exist. Because they're different, right?
Okay.
What about here?
For what?
What is my limit approaching from the negative side?
2.
Eh.
2.
Non-existent.
2.
Huh?
Wait.
Where is the limit? Where is it trying to go from here to here? It's trying to go, it's 1, right?
2.
But
That's
what
the
about
x value. I'm looking for the y value.
2. 2.
So as I'm approaching here, it's trying to get to 1. So the limit is 1
Oh, because then it jumps
from
up
from the left-hand side. What about from the right-hand side?
Wait, why is it one?
What about that dot that's up there?
It's still 1.
What about the right-hand side?
3. 3. 3. 3. 3. 3. 3. 3.
From here, I'm
2.
approaching
2.
what?
2.
One.
2.
1.
2.
Right? It's 1. So therefore, the limit
2.
One.
2.
is 1
1.
at 2.
What?
So the limit is 1 at 2. Okay? So in other words, the limit at 2, whether it's this guy or otherwise, right, limit as x approaches 2 from the negative side, are the same. They're both 1. However, the value itself, not 1 but 2, right, because it's approaching 2 here, is going to be
Okay.
2. The function value is 2.
Oh.
Because it's defined as 2, right? That's how the function is defined. Okay, so this is a classic example of a discontinuity, right? Where
Need to pick
the
up your
limit
pencil.
exists, but the function value itself is up here. And you can see as a discontinuity, right? In order to draw it, you're going to have to go like this. You have to lift your pen and then come back and go like this, right?
Uh-huh.
Okay, so let's look at 3. At 3, my right hand limit is what?
2. 2.
From the right hand side, I'm coming this way, so it's going to be 2.
1.5.
2 up here, right? It's going to be 2, that's 2. All right? So over here on the left hand side,
2.
what is it?
2.
2.
So then we have a real limit there.
So you have actually a limit, and you have the value that coincides with that limit.
So there is a
Therefore, it's
limit.
actually a continuity here.
I
Right?
give up. I give up.
Okay?
So they're both the same age.
What?
Oh, because it's not an open circle. If it was an
Yeah.
open circle, then it
Right.
would
If
be
I
a limit.
if I went like this, it would not be a discontinuity. It would not be a continuity, right? Because again, the value of the function itself would be different, right? Okay, so there's a distinct difference here between the limit and the value of the function itself.
So you have to write both?
So, in this part right now, all we're talking about is whether or not the limit exists, right? For the limit to exist, what has to happen?
Pick up your pencil.
Nope. That's continuity. We're not talking about continuity here. We're talking about the limit. For the limit to exist, we said the theorem number 3 says that they have to approach the same value, right?
From not different directions.
So if we even come from different directions, they have to go like this. If you are like this, then there's no limit.
There could
Then
be
it
an
would be a
asymptote.
DNE, right? Does not
So we're
exist.
talking about
Okay.
multiple functions.
But if it goes like this, it could have an asymptote, but it wouldn't have a limit.
So each of
Could
these
have.
line segments are their own
Okay.
function?
Huh?
Each of these little segments are their own function then?
Well, it's one function, but it's a
Piecewise.
piecewise function, right? So they're defined
That makes it.
differently within different intervals. Okay? All right. So that's that, and then we're gonna do one more, and we'll go straight to example number 9. If you look at example number 9, you have a function that we had actually talked about something like this before. Anybody remember what this is called?
The squeeze thing? I'm just kidding. Oh.
Oscillation.
What kind?
Dampen.
Dampened oscillation, right? It's dampened oscillation because it is bounded. Does it say there? It doesn't say
No, I
there.
didn't even do this.
It doesn't.
You guys don't remember that?
Just remember it.
X squared
I
times
don't
over
you
X.
remember dampened oscillation, huh?
It's like sound.
Y'all ever remember that?
I remember it. I just don't know where you pulled it from.
Just the function? What's the function?
It was like a,
Yeah.
I don't know, I guess it was so small.
it was impressive.
X approaches 0, 1 over sine x. Okay? And I'm trying to find the limit as x approaches 0. Okay? Go ahead and graph this for me.
Doesn't it tell you what it equals?
Does what?
It tells you what it equals.
Where? Who?
Mm,
Oh, the book tells you.
No, you're trying to prove it. You're not trying
Yes,
to find
I'm
it.
trying to prove it.
yeah. It's just a straight line for right now.
No, it's
No,
not.
it's got a little.
There's a little thing up.
You have to zoom in a little.
Ooh.
Okay, you can see the dampened oscillation there, correct? Because it's oscillating between y is equal to x squared and y is equal to negative x squared, right?
Doesn't equal 0.
Okay, so here we go. So let's get this. Sine 1 over
It's
x.
a little shifty.
I know.
What is the maximum value and what's the minimum value?
You know.
Something like that.
Huh?
Infinity.
Any sign is going to be between 1 and negative 1, right?
Oh,
It's
so the-
bounded by 1 and negative 1, correct?
Okay.
Any way you look at it.
Unless it's-
Okay. So now I'm going to multiply everything by x squared.
Okay.
And I can do this without flipping my things because x squared is always positive.
But if it's negative, you flip
Okay,
it.
so now, limit as x approaches, I'm going to put this on every single one of them. Because this is actually what we're trying to find, correct?
Okay.
X squared sine 1 minus x, limit as x approaches 0, x squared. What is this value?
0.
Wait. You just add a limit to alpha.
Yeah, because I'm trying to find the limit. This is 0, right? X goes to 0, this goes to 0, correct?
Mm-hmm.
Negative
0, right? It's 0, right? So this guy is squeezed between this 0 and this 0, so therefore this can be nothing but 0.
True 0.
So we are taking this guy and we're squeezing it from both sides, and that is why the theorem is called the
Dampened oscillation.
squeeze theorem, right?
But when you trace it, it doesn't equal 0. It's because it can't equal 0? Or it, because the limit is it's trying to get to 0, but
It's
it
trying to
can't
get
reach
to 0.
0.
It's trying
So
to
if
get
it's
to 0.
squeezed between two zeros.
Correct, it has to be
it
0.
How does it-
All right, we're done for the day.
Woo!